What I want to do in this video is talk about graphing. This is section 5.8. We're going to do some of these problems. We'll do 2 of these on this section, how to graph polynomials. We're getting near the end of chapter 5. It's not that difficult, but I want to make sure because of the snow days, we've missed some school and I want to give you some examples on this. When you do the work, you'll have something to refer to. We'll go over these when we get back in school next Tuesday, but until then I want to make sure you're giving these a try. So what we're going to do is do 2 graphs of different polynomials. Alright, so you can follow along with me. This is from the section 5.8 in the book. This is page 390 or 389 around there, and then we'll talk about the problems. Now, let's do a first one as an example. We have a polynomial. This is f of x. F of x is equal to 2 times x minus 1 squared times x minus 4. Okay, well what are these? Before we do any graphing, what are these things? These are, remember, your factored roots. So it looks like synthetic substitution was done on this thing once, and then there was some factoring done. We have 3 roots here. Of course, 1 is repeated. Now, when we graph these things, the roots mean where y is equal to 0. Okay, because if any of these are 0, the function goes to 0 because 0 times anything is 0. That means that these are graphed along the x-axis. These are just our roots, where this thing crosses the x-axis. Alright? Now, x minus 1, if it's inside the parentheses, you have to flip the order. So this becomes x equals positive 1. X minus 1 equals 0. Therefore, x equals positive 1. So one of our roots, in fact a double root, is right here. We're going to talk about what that exactly means in a minute. But if you graph this on 1, 0. The other one, x minus 4. That means that it's x equals 4, because x minus 4 equals 0. So x equals 4. 1, 2, 3, 4. That's right here. Okay, now these are our 2 roots. We don't have a graph yet. We don't know what this thing looks like, so we need to pick some points. We're going to pick points on either side of this thing, just a few of them. Now, first point we'll pick is 0. On the left side. We have to pick some in the middle. This is 1, 2, and 3. We have 4. We don't need to pick that. And then 5. That should give us a general feeling for what this graph looks like. So what we need to do is plug 0, all these points in here, and find out what the y values are, and then we'll graph them. Let's do that. 0 minus 1 is negative 1. Negative 1 squared is 1. 0 minus 4 is negative 4. 1 times negative 4 is negative 4. Negative 4 times 2 is negative 8. I'm not going to draw this out here, but you can work it out on paper as well. Now, 2. 2 minus 1 is 1. 1 squared is 1. 2 times 1 is 2. 2 minus 4 is negative 2. 2 times negative 2 is negative 4. Okay. 3. 3 minus 1 is 2. 2 squared is 4. 4 times 2 is 8. 3 minus 4 is negative 1, so 8 times negative 1 is negative 8. Okay, we're seeing a pattern here. 5. 5 minus 1 is 4. 4 squared is 16. 16 times 2 is 32. 5 minus 4 is 1. 32 times 1 is positive 32. Okay, we've got our 5 points. Let's take a look at what this thing looks like. 0, negative 8. 1, 2, 3, 4, 5, 6, 7, 8. That's here. Alright. Then we have 1, 0, 1, 0. Then 2, negative 4. 1, 2, 3, 4. That's right here. Then we have 3, negative 8. 1, 2, 3. That's down over here again. Then 4, 0, and then 5, 32. I'm just going to put this way up here. Okay? Now, what does this thing look like? Got some points here. We're going to go from left to right. Notice, this is a 3rd degree polynomial. 3rd degree. That means it's odd. That means if we think about member end behavior, the one end will be positive infinity, and the other end will be negative infinity. Left is negative, right is positive, because this has no negatives in front of it. Okay, so remember, don't forget the end behavior. When you're drawing these things, you need to know the end behavior. If it has a positive coefficient and it's odd, then what we're going to do is have the positive infinity on the right, negative on the left. If this one is a if this had a 4th power, then we'd have either both positive infinities or both negative infinities. So we know that this is going to be down here at negative infinity. Now we're going to come up. We're going to turn at this point, turn up here, and go up all the way up here. Okay? Now, obviously, I'm doing the side, but you can kind of see this should be straight line. Okay? so I'm just kind of doing this on the side here. It's difficult. But we know that this goes down and this goes up. We have a negative infinity here and a positive infinity here. Now, how did I know to turn here that this was the highest point? Well, notice we have a double root. Okay, x minus 1 squared. That means that this thing passes twice. Well, the only way it could pass twice is if it goes, well, once on the up and once on the down. That means if you have any of these double roots, you know it's going to be a turning point. This is called a turning point. Okay? This is a turning point. It's where the graph turns. There's another turning point. Can you see it? That's right here. This is the other turning point. Now, this is not a root because it's not along the x-axis. But it is a turning point. The graph turns there. Okay? So we have two solutions because there's a squared, so the turning point is at 1 of them is, and the other one isn't a turning point, just go straight through it. Okay? Now, this is the minimum value is minimum infinity, the boundary. So this function will continue to go down. The positive highest value is positive infinity. That's the end behavior. But we have what's called local minimums and local maximums. Okay? So think about this in terms of, in the graph, where are local minimums, local maximums? Well, a local minimum is right here because this is a turning point where it gets no farther down. So if we think about like the mountain ranges, this is a smaller mountain, but it's still bigger than a hill. Okay, it's not Mount Everest, but it's still significant. We call it a mountain, even though it's not the highest one, or the lowest one in this case with a valley. So this is a local minimum. All right, local minimum. Now, the local maximum is right here because you notice there's a turning point. Anytime there's a turning point, it's either a local min or a local max if it's one of the highest points there. So this is a local max, and that gives us our two turning points, local maximum and local minimum. They're not the absolute max, absolute min, but they are the local max and local mins. So this is what we got from graphing it. If you know the points here, if you have the root points, then you can find out where it's going based on end behavior on the ends and in the middle. Okay? Let's try one more.